Hi, welcome everyone. I am Sarah Christoff with the clicker. Cool. I'm a staff software engineer at Edera. You can just check us out at edera.dev. I am the founder and member #1 of the Leslie Lamport fan club, which hopefully you all joined today. And I'm the Porter maintainer. Come check us out there too, porter.dev, and a tech lead of Tag App Delivery.
And I'm Nick Jackson. I'm a developer advocate at Hashicorp and the inaugural but one member of the Leslie Lamport fan club, which I think the membership is currently up to 3, maybe?
3 with Lamport himself, of course, joining his own club. So today we're about to teach you, kind of give you like a distributed systems history 101. Our agenda today is we're going to cover consensus, consistency, concurrency, and clocks. Nick and I will be trading off, doing a little bit of a history lesson for you as well. And so Nick will kick us off with not this part. So do you ever wonder why we're here at KubeCon? So why do we care about like an 80-year-old man's work from like the 1960s? Lamport has published about 200 papers. You can check it out on leslielamport.com/AzureNet. And he is often quoted as the father of distributed systems. He is the founder and creator of Paxos, which influenced Raft, which you should know because of etcd. And he is also the creator of TLA+, which is a language to help design and test distributed systems. So most of the common underlying systems we have today are influenced by Lamport.
And that leads us nicely up to consensus. So to kind of like make things a little bit more interesting, what we want to do is kind of set a bit of a theme. And we're going to derive our theme from one of the most famous papers that Leslie Lamport wrote, which is the Byzantine generals problem. Now, if you've ever read any of Leslie's papers, he always tries to kind of weave this story into things to try and help with the understanding of things. And we're going to just do that. So Byzantine. Well, so Byzantine was formed by Emperor Constantine, and it was based in around about the 4th century sort of BC, but on the old Greek settlement of Byzantium. Now, Constantine, being the humble man that he was, named the city after himself, called Constantinople. And if anybody's familiar, Constantinople currently stands where Istanbul now is. But it didn't kind of end there, because in like the 6th century, Justinian, another sort of Roman, decided that, you know, the Byzantine Empire was growing. It's pretty big, but we can make it better. And he had an aim that sort of to kind of build up this empire and to actually take over the western side of the Roman Empire, which included Rome itself. Which leads us into our main characters. So we have Emperor Romanus. So Emperor Romanus, in the 11th century, was the emperor of the Byzantine Empire. Now, he was married to the Empress Zoe. Now, Romanus met a somewhat short end of his life. Allegedly, he was poisoned. I'm pretty sure it had nothing to do with Zoe's lover, who was Michael the money changer. Maybe it did. Now, Michael became the emperor of the Byzantine Empire. He wasn't so great at the whole governance side of things, pretty good from a military perspective. He then gets John the Eunuch, who is his brother, to help him out. George Manolakes, well, he's one of the top generals of the time in the empire, so he's going to be a prominent character in our story. And then we have, like, as an interesting twist, Harold Sigurdsson. And Harold is Danish. He's actually a Viking. So he's leading a band of Varangian mercenaries who are helping the Byzantines. Later also became the king of Denmark. And it leads us into our problem of the two generals problem. So at the time, the city of Syracuse, the Byzantine Empire wanted to capture Syracuse. So, well, Michael says, George says, look, I want you to go capture this city. And George says, yeah, sure, no problem at all. I'll go. I'm going to take Harold with me. We'll get this done. Now, they formulated this plan. They said, right, what we're going to do is we're going to say that if one of us attacks, then we're going to get defeated because we'll be overpowered. If both of us attack at the same time, then, you know, we're going to take the city. And if one of us, if we both decide not to attack, then obviously we live to fight another day. Now, this problem is actually unsolvable in computer science, because one of the issues that they had was they needed to be aware that they were both going to sort of attack at exactly the same time. Now, they're both on opposing sides of the city. So originally, George was like, well, I'm just going to send you a message. So George sends a message, hey, I'm going to attack at 10 o'clock. But he needs to know that Harold's also going to attack. So he says, well, send me a message back saying you're going to attack as well. So he sends a message back and he says, well, send me a message back to say that you got my message. And this goes on and on and on. And ultimately, they can't achieve a consensus to be guaranteed that both of them have got the same message and the same data and they're going to attack at the same time. So two generals problem is not solvable. And if we kind of look at that, you can see there that it's just not possible to kind of whichever way you want to cut it. So then, well, Michael says, well, I've got a better idea. What we're going to do is I'm going to send a messenger. I'll make the order. I'll send a messenger to you, Harold. I'll send a message to you, George. And then when you get the message, we'll attack. And Harold looks at that and goes, well, what happens if one of the messages gets intercepted? So, well, oh, okay. I mean, that's possible. And Lamport mentions this as a traitor. And if you think of a traitor as something which could be just a failing node or some node that's misrepresenting a piece of information. So then they sort of say, well, I've got an idea. So Harold says, well, I'm going to send a message to George with your instruction. George says, I'm going to send a message to you, Harold, with Michael's instruction, and then we'll be good, because then we'll know exactly what's going on. But it doesn't work, because in the presence of having one traitor, you can't agree consensus. So for example, if a traitor intercepts Harold's message to George and says retreat instead of attack, then George now has conflicting information. He has one attack from Michael, one retreat from Harold. So in light of not being able to kind of form consensus on that, he decides he's going to retreat. Well, Harold, he attacks, and it's a problem. So Michael says, well, look, we need a better problem. We need a solution to this. So he speaks to John the eunuch, and says, John, what can we do? This was my idea. And John says, well, I think we can kind of sort of make this a little bit more interesting. So we know that 3 generals doesn't work. But what if we've got 4 generals? So then John the eunuch looks at that and he says, well, if we have a 3rd general, in Michael the commander, then we can suffer one of the traitors, because when the messages are being passed around, if the traitor sends a kind of a misleading message to any of the other 2, then of course they can still recover that, because they have 3 other messages which enable them to kind of come to consensus. And you can see here that the first round, obviously, the commander sends attack. They then validate that with the 2nd round. The traitorous messages from John obviously get to George and Harold, but they're not used. There's an overwhelming kind of attack. So they attack and it solves a great day. And if you kind of model that with the commander, and let's say one of the commander's messages is misinterpreted or is intercepted, it still works. So the solution on that, when you're kind of looking through what Leslie says, he says, well, to achieve Byzantine consensus, what you need is 3m plus 1 generals, where m is the number of traitors. So we've kind of proven that works for 4 generals with 1 traitor. But what if you've got 2? Well, then you need 7 generals, and if you need 3, then you have 10, and 4 is 13. But the formula works. Now, I apologize for that slide. It might be easier for you to read than I can read. But if we look at the data for 7 generals, then what we can see is that we have a sort of a round of voting. We can't achieve consensus. Not all of us have got to agree on the same action, which we can't do in light of a traitorous commander. And then after a sort of a 2nd round of voting, when everybody sends everybody else their kind of data, we still can't achieve consensus. I was like, okay, but the formula says 3m plus 1, and I've got 3m plus 1, but I've on my second round of voting, I haven't achieved consensus. And that's because later in the paper, Lamport goes on to mention that actually you've got to have a number of voting, which is kind of in line with the number of traders. So we need 3 voting rounds. The third voting round, again, it's recursive, so everybody sends everybody what everybody else has received, and ultimately what you can see is that by using that information, you can remove the kind of the traitorous nodes, or the nodes which are sending the data incorrectly, and you can achieve consensus on decision. And that kind of comes down to this formula, which is also later in the paper, which says that in addition to the 3m plus 1, you need t plus 1 voting rounds, where t is the number of traders. And I'm not going to get into why Leslie uses t and m for trader. That's a question for him. So let's kind of move on. I was going to show you a little demo of that in action, but do you trust me that that works? I mean, I can show you the demo. Should I show them the demo?
Show them that you worked hard on that.
What if the demo doesn't work?
Well, that's Lamport's problem.
I'm going to try and show you the demo. This is not easy.
You got this.
So we'll show you the kind of a very simple demo. So what we have is a commander. We've got the 3 generals. So with the first voting round, what we've got is the commander there. Zoom it in. Speak up. Zoom it in. I'm sorry, I've got bad hearing.
It's good. You're good.
Okay. So then after the first round of voting, you can see that there's no consensus. So what's happened is the commander has passed the message of attack to each of the generals. They've then gone and tried to kind of form an opinion on that. And John, of course, has received retreat, so no consensus. So if we then go on to the second round of voting, then you can see now that we can achieve consensus. So even though that John has sent retreat to Harold and George, then actually it's still possible to achieve consensus. And if we kind of model that with the 7 generals, and if there's a little bit of time left over, I can show you that later on. But the formula works. Now, what's amazing, what I absolutely love with this and with many of the other papers that are from this kind of era of Lamport is 40 years ago, over 40 years ago, he wouldn't have had a computer on his desk. All of this kind of theorization and all of this formula would have been based around pen and paper and obviously tested in a lab, but I find that incomprehensible.
I think it is very cool. Can you fix?
Oh, you want your speaker notes?
Yeah. Cool. And now we're going to get into consistency, specifically consistency models. So, going back to John the Eunuch, and you got it? Going back to John the Eunuch, we're going to continue this scenario, which is that basically consistency cannot be achieved without great communication. And when running a siege, you do need good communication. Just drag it.
I can't see it.
Do you want me to do it? Speaking of great communication, just like host presenters on stage. So, right, consistency and consensus go hand in hand, and they cannot be achieved like a good siege without good communication. So what we're trying to achieve here is that all messages must be sent in a specific order to gain this knowledge of whether we should attack or not attack. Cool. So in typical Michael fashion, he asked John the Eunuch, hey, we have these messages, they're getting sent out of order. What do I do? How do I make sure that we achieve consensus through consistency? And I've kind of tweaked these a little bit so that they can kind of adhere to our story, but underneath is the actual like technical term, and on the top in the big letters is for our story. So John the Eunuch identified 3 key areas that we had to focus on here. And we wanted to focus on message consistency, which is data consistency, soldier availability, which you can think of like as node availability or pod availability, whatever you want to add as a Kubernetes term onto this, and then tolerance to bad actors. That one I fudged a lot because I don't know how to like do tolerance to network partitions or like dealing with like network and connectivity in the 1800s. We're in the 1800s, right?
Oh,
Oh, fuck.
10th century. Maybe 11th.
I don't know history. I'm from Pennsylvania, okay? So what he did come up with was 4 models for us to kind of adhere to. We have eventual, weak, strong, and sequential. In our world, with our consensus types, we usually stick with eventual, which is basically, I just realized, the planets thing is on purpose. But yeah, basically we have 4 different types, and in Paxos and RAF we usually use eventual consistency. Strong consistency is very rare, mainly because it is very hard to do in distributed systems. And weak is usually what I tell people to do, but customers hate, because weak is basically saying, we'll eventually be consistent, but I can't ever give you any guarantees. So in eventual consistency, we can see here, there's only a guarantee that the message would be delivered, but there's no promises on like if the inquired message would be received in the most up-to-date way. So a good way to frame this is that you will eventually get the information. Whether it's on time for your attack, I don't know, but you'll get it. For weak, there are no guarantees. It just basically says like a message could be delivered or it couldn't be. You might get it or you might not. Strong means that basically we ask that every read or message is read, and then we get a confirmation, kind of like SYNAC, from the general, and we will return the most up-to-date information no matter what. Sequential is weird and fun, and the best way I've found to describe this is with Facebook, which does not fit our model here because there was no Facebook in 400 BC or whatever. The dates keep changing. So basically the way that I have found the best way to describe this is if you were on Facebook a long time ago, you might have left a comment on a post. You might have noticed after you refresh the page that another comment has come before your comment. This is because they were sent at the same time, and what happened was timestamps were consolidated after they had refreshed. And so sequentially, like it gets into order, but it just takes a little bit to refresh. Cool. Going a little fast. So, consistency models are used in everyday computer systems. They're most commonly used in databases, which is why I referenced Paxos and Raft. But in militia and sieges and that type of stuff, they're also incredibly important to keep data up to date and to keep sieges from happening and armies from winning. So in a Lamport-esque state of way of saying this, knowing consistency models will help you understand the guarantees and restrictions of a distributed system and understand how you should design your system. This is my favorite one. This is concurrency. It is my favorite because I get to have this one, which is that basically Lamport says in teaching concurrency paper that he's never taken a comp sci course. Me too. We have so much in common. So today I will attempt to teach you comp sci 101 from his one paper. I've read many a paper, but of his. So welcome to comp sci 101. And the first question is, what is a computation? So if you're studying the system or the theory of computers, like what does it even mean? And for the purpose of this paper, we say that a computation is a series of steps. But that kind of brings us to this question, which is, what even is a step? And typically for the paper, we say that like a step is a transition from one state to the next. Now we're going to get into some true Lamport-isms, which is basically he talks about how the verbiage we use in discussing computers is very Western, and we focus on like verbiage and actions, like a verb, and basically states that like the computer only thinks about like transitioning steps and not actually how we think of it, which is the state it is in. So we have to think of computing as transitions and not state, right? The end states. He pushes us to reframe our thinking and speaking about computation devices or just computers so that we can better understand concurrency. So hopefully this little bit of vocabulary will help you understand the rest of all of this. Now, and an invariance is a condition that is always thought to be true throughout the execution of a program. In simpler terms, it's like a thing that never changes state even when a transformation is applied to it. And a simple way to think of this is if the base case is n equals 1, then the inductive invariance case of this is n equals 1 and n plus 1. Okay, this is a really good quote from the paper, mainly because he says she in it, and like, I'm really happy. So now that we have like the foundation on this vocabulary here, and we can understand what a computation step and invariance is, we can kind of summarize concurrency as the way to handle multiple steps, being able to switch between them and continue them running. Note, this is kind of different from parallelism. I'm not going to get into it. Talk to me after class. Okay. I'm not going to say his name. I don't know how to say it. You should read his paper. He, in 1965, proposed this paper, which is thought as the first introduction into concurrency. And basically, he proposed the requirement of mutual exclusion for concurrency. In Go, you might be familiar with mutual exclusion based off of mutexes. We'll briefly touch on mutual exclusion, which is a rule that specifies that only one piece of code can enter a critical selection at a time. So basically in this photo, really quick, you see that we're doing a removal op. We're trying to remove I and I plus 1 at the same time. But when we do that, we only remove I, not I plus 1. So the resultant linked list here, it still has the stuff. Like the two removal ops did not happen correctly. So, Lamport and a lot of other friends, they all have like a lot of different papers on this, created a paper that was supposed to help teach concurrency and satisfy mutual exclusion called this right here. Basically, he calls out that his algorithm satisfies starvation freedom. Starvation is basically meaning that every process that tries to enter the critical selection of code eventually does so. And the bakery algorithm that we'll talk about a little bit, it is starvation free. So, and Lamport in all of his papers does a really good job of breaking things into real world examples. So the bakery algorithm is something that hopefully most of us can relate to. When you enter a bakery, you take a number from like the little red ticket guy, hope they still have those in Europe, and you wait for your number to be called. This is considered the non-critical section. You're browsing the wares of the bakery, you're looking at baked goods, you're hanging out. Maybe you're talking to other customers or you're on your phone. The lower number, so the lowest number that you pull from the ticket guy, will go from lowest to highest. Basically, if a customer halts, I don't know the right word for a halt, like are you just gonna drop over? I'm not really sure. But if a customer halts, they will exit the bakery if they're in the non-critical section. Now, when their number is called, they enter the critical section, which is when you go place your order for bread. And that is basically saying a customer and a baker can only talk at one at a time, and that has to complete. So now Lamport goes into like the deconstructed bakery algorithm to go into like ways you can implement this in distributed systems. It gets really math heavy. I would encourage you to read it if you like algebra. Oh, and I think it's very fun that he is able to talk about mutual exclusion without using the word semaphore even once. Boop.
Which leads us up to clocks. So clocks, in terms of Lamport clocks, it's actually a really, really old concept. So when kind of Leslie Lamport was kind of looking at clocks and things like that, he was looking at primarily around how you would solve concurrency in a sort of single processor architecture. And this is back late 70s, very early 80s. But even back then, at the time, they're starting to think about the fact that systems are becoming distributed. And that like literally blows my mind. But conceptually, if we jump back into our story, what we have as an example. So Michael is going to send the message to George and also to Harold to kind of make that attack so they can take the city of Syracuse. So that message gets sent. So George gets the message, and it says attack at 10:30. Now George, because of his vantage point over the city, says, well, you know, this is not right. If we attack at 10:30, we're going to get toasted. What we need to do is attack at night and attack at 8:30. So he sends that message to Harold. Now, Harold gets the message from George, says attack at 8:30. But the message that was originally sent by Michael arrives after that. So in terms of Harold's mind, he's now going to attack at 10:30, the original message, because of the problem with this message ordering. Now, John has the same issue. So the problem again, we need this consensus. We all got to attack at the same time. It's not going to happen. So Lamport proposes an incredibly simple solution to this. And he says, what we're going to do is we're going to have a message ID. So when an event occurs, that event being that we're going to send a message, we're going to add the Lamport time, the sort of the timestamp on there. It's going to become message 1. When sort of George receives that, what he does is he's going to increment his clock by 1 to kind of be 1 there as well. So everybody's now got a message ID. So in the instance where we had this sort of problem before, where the kind of the message ordering came out of whack, it no longer applies, because now when Harold gets the message from George, it's got an out of sort of band order. So it's got an ID number which is sort of the same. So he can, by using that, he can determine that George's order takes precedence over Michael's, and the Michael's order should be disregarded because of the message ID being lower. And what kind of the guarantee there is that you get sort of, so given 2 messages with the same timestamp, same Lamport clock, you've got to use a tie break. So how do you kind of determine? So if, say, George and Michael's order both have exactly the same message ID, what should the receiving general do? And in this instance, you can use a number of different things. A common approach that Lamport says is to use like a lexicographical order. You could just say, well, hey, I'll use the node name, and anything that's alphabetically takes precedence is going to take precedence as an order. This can also be a predetermined order. You could kind of say, well, hey, Michael is the commanding general, so he will always take precedence. And as long as each of the recipients of the message understand this, as long as they all apply this sort of common framework, then in the instance you end up with 2 message IDs, you can determine what to do. Now, vector clocks are a kind of an advancement of a Lamport clock. And what vector clocks try to do is they try to kind of solve the problem of concurrency. And kind of like Leslie, when he's thinking about those things, didn't necessarily have the problem. Vector clocks become more complex because what you're doing with a vector clock is each individual node and its clock ID is sent with each individual message, so that when you receive that out of band, you can determine that, well, hey, node A has never received message 1, and therefore you can determine the order better or determine the concurrency. But if you kind of look back at that and you look at a vector clock as a more complex, it requires more data, Lamport clocks are still widely used. Just as a kind of a show of hand, does anybody work on a system which uses a Lamport clock? There's quite a few people, right? Like it's a 40-year-old concept that was developed on a piece of paper, and we're still using it today.
Cool. So we've covered a lot of like very in-depth topics very briefly for you all today. And so in a world very, very far away, I might have given a talk about Raft, Paxos, and the beginning of all those things consensus. And in researching for that talk that I gave 6 years ago now, I discovered distributed systems drama, which is, if you like reality TV, Kaylin, then you know distributed systems drama is the best drama, mainly because it's a bunch of nerds fighting over white papers. And so basically there was some controversial takes that Lamport was just too fun because he enjoys taking incredibly in-depth topics and tying them to history and real world scenarios. Hell, I mean, Raft exists because Paxos is too difficult to understand. So Leslie Lamport, with his almost 200 papers, has he been right about these topics? And to give a personal antidote, there might have been a time, there was once a apprentice software engineer who moved one line of code that was setting a timestamp. And that might have caused a multi-million-dollar outage that brought down a very important stock trading company, all because one timestamp was moved. And it
Sarah,
was, yes.
Would that apprentice software engineer be in
Was
this
it
room?
you? Was it you?
No, it wasn't me. I'm way too old to have ever been an apprentice. In the
Stocks
last,
were around
last
when you were
millennium.
around. She might, or he might be in this room. And that apprentice software engineer only found out that they broke that code on a retro that they were on and was incredibly embarrassed. Anyways, if the clocks were built differently, would have that company have fallen into many lawsuits of that system breaking? So I can tell you that for me, as a person who wasn't able to do like a computer science course, the answer is yes. Leslie Lamport is right about these 200 papers. He was right about how he wrote them. They're fun and approachable, even though the numbers scare me. And I think we would both like to know if he's helped you as well. Was he right for you as well? So you can find us here. Nick, do you have any closing comments? We're over time, but.
No, predominantly, I think, we've talked about a lot of Leslie Lamport. There's some incredible people who are working in our industry who are equally as important, and Leslie is but one of them. But he's definitely, I just think his work is really approachable. So if you have the opportunity, just go and maybe watch some stuff on YouTube where somebody's explaining some stuff. Dig into the papers. Have a try. Maybe play around and try and solve some of the maths inside of those.
Yep.
And it's going to benefit you because the systems are still using this work.
Yeah. So here's all the papers that we referenced today. Just if you want to take a little screenshot, we'll upload the slides somewhere on the internet, or they're on like the KubeCon website. I don't know. But thank you so much for your time today, and I hope you have a good rest of your conference.
Thank you.